We're going to talk now about what is the relationship with the change in gift-free energy and the equilibrium. So now we know delta H equals delta G equals delta H minus D delta S. So let's draw now what we call an energy profile of a reaction. Now in the y-axis, I have my gift-free energy. And here I'm going to say reaction coordinates. So next, we're going to be drawing the profiles to say that I have now, this is my reactants, and this is products. So now here, let's put an R here, reactants and products. Notice that in this drawing, if I'm going to do the change in delta G, the delta G is calculated, say, as free energy of the products minus the free energy of the reactants. And notice it's going to be this number here. That is the free energy, that amount, right? And minus all of these. So when we do that math, it turns out that delta G, this is this minus that, is a negative number. And that when a reaction has a negative change in gift-free energy, we call that exergonic. All right. And now let's do another profile. Now say that I have a bit different. Let's see. All right. Now I have again gift-free energy. I'm going to make an arrow. This corresponds to that. Not to be confused with what I'm writing over here now. Now, in this reaction, say now that I have reactants here and products here. Now, R and P, so reactants and products simply. And then we're going to say this is gift-free energy reaction coordinates. So that shows how the reaction progress from reactants to the products. Now, if we were to calculate the change in gift-free energy, what we need to do, subtract the gift-free energy of, so products minus reactant. What is the gift-free energy of the products? Well, I have this much. Say, this is where the products are. Minus this. So these amount minus these amounts. So in this case, the number is positive. So for that profile, for that energy profile, we say with a positive change in gift-free energy, we say this is enegergonic. And analyzing what's the meaning of that. Notice here, products are more stable than the reactant. This reaction is product favored. If we will have in the equilibrium more, in other words, more product than we have reactants. This, however, products are less stable than reactants. And so we say at the equilibrium, we will have more of the reactant, the position of the equilibrium. Now, the position of the equilibrium, we have an equation that actually can relay that. Now I'm going to write that the equation of a general reaction. Say A plus B to give A plus B, and let's do this, C plus D. So these are my reactants, these are my products. Okay, and so we define, and that we learn in general chemistry that we define the equilibrium constant of this reaction as the product of a concentration of these two species, the products. Well, here we're assuming that all stoichiometric coefficients is 1, 1, 1, 1. If we do have other coefficients, then we need to put the coefficients here in the equation. But for this example, this is the equilibrium constant. So now, the equilibrium constant is related to the change in gift-free energy. So the change in gift-free energy is negative, and here is RT, the gas contents. So, and this is natural log of the equilibrium constant. And in other words, we can say that the equilibrium constant can be calculated taking anti-log here as E and elevated to negative delta G over RT. And so with that, what we have then is the a way to calculate the give-free energy. Now, in the give-free energy in the relationship with the equilibrium constant. So let's think about what will happen, and I'm going to remove that. I'm going to draw a third profile, actually. So this is my reaction. So R was here A and B, in products is C and D. Let's see what happens if I have another profile. Now, in this case, again, reaction coordinates and give free energy, right? Increasing in that direction. But now say that I have a reaction in which, well, here my reactants and my products are at about the same level of energy. So here my reactants, we know they were A, B, C, D, about the same energy. What happens when we go to the equilibrium constant? Well, we see that here the change in give-free energy is approx 0. Because remember how we calculated that? This approx minus that. It is approx the same. So change in give-free energy is about 0. In terms of this expression, we also see that, well, we will have about the same, being then of the same give-free energy, we will have about the same amount of C and D that we have AB. So what that means is that the equilibrium constant is approximately 1. So that's the meaning of that. So if we don't have change in give-free energy, then the equilibrium constant is 1. We're going to be looking at more numbers about relating what is a change in give-free energy in the case of exergonic and endergonic in the equilibrium constant. But here we have a reference. 0 change in give-free energy, the equilibrium constant is 1, so it's neither product favor or reactant favor. It's just equilibrium. And we have about equal concentration of reactants and products in the equilibrium.